This is the first section in the further kinematics chapter, and it covers a lot of stuff that you've done before, but here we combine SUVAT with vectors, and we actually use vectors in 2D, the I and J unit vectors. So you've come across those before. I and J are unit vectors. You know that you can represent a vector like this, let's say a coordinate like 3, 4 position vector, you could represent as 3i plus 4j, or you can represent it as a column 3, 4. Now I've put, not a line, I've put here ij versus column because you may find that on some of the questions that we do that you may prefer to write it in the ij form or the column form. They're equivalent. Depending on the question, you may say, right, they give you information in ij, you convert it to a column, and then you do the working as a column and convert back, or you may be given as a column, you convert it to ij. All depends, but sometimes it may be the column working is easier. Now we can use SUVAT with vectors, SUVAT. Now time is always going to be a scalar, so that will just be a single number. Acceleration, well, that can be a vector, and we can write that as a column or ij, and that would be meters per second squared. Initial and final velocity, these can be vectors as well. Yeah, meters per second. And displacement can also be a vector as well, and that will be in meters. See, the only thing that's a scalar would be time, and you can use vectors in any SUVAT equation. And as I say, when you put these vectors into SUVAT equations, you may prefer the column method to work things out. Now this thing over here, this massively enlarged text over here, r equals r0, what's that? Well, you may be at times asked to work out the new position of an object. So r0 here, this is a position, and this r0 represents the initial position of an object. Yeah, it represents the initial position of an object, so that's going to be maybe in ij or column form. Vt, that's velocity times time, that represents, well, if you do velocity times time, you get the displacement of the object. So if you've got the initial position of something and you add its displacement, what do you get? You get its final position. So r here represents the final position of this object. So if we just think initial position plus displacement gives us final position. Initial position r0 plus displacement, velocity times time gives you displacement, will give you the final positions. This is very useful for questions that we're going to be tackling in these kinematics type questions. Right, what do we have here? A particle starts from a point with position vector 3i plus 7j. Okay, so if that's where it starts, that's r0, and moves with constant velocity 2i minus j. So here's our value of t as a vector. Find the position of the particle 4 seconds later. So what are we finding? We're finding its final position, and final position equals initial position plus displacement. Yeah, I'll actually write some of these things down. So final position, final pos equals initial position, initial pos plus displacement, which makes sense. You start somewhere, you move a bit, and you finish somewhere. So our final position, which is going to be r, which is going to be, we're working out, the initial position is r0, and our displacement is velocity times time. So our initial position is 3, 7. Now I'm going to write this as a column vector. Plus velocity times time. So the velocity is as a column vector 2, -1. 2, -1. And that's going to get times by 4. Now all we need to do is to work that out and we get our answer. Yeah, and you can see in the column it's nice and easy. So 3 plus 2 times 4. 3 plus 8 is 11. Bottom row, 7 plus -4. In other words, 7 minus 4, which is going to be 3. So that's the position as a column vector. Let's write it as I and j. So this final position, the answer they want, is going to be 11i plus 3j. And yeah, that's just going to be its position. So we don't put meters or anything like that. It's just a position. Well, do we write m meters? I suppose we do, because it's a position, isn't it, relative to the origin. So we should put meters. Any position or displacement should be in meters, really. Right, part B. Find the time at which the particle is due east of the origin. Now sometimes a diagram helps, like this. So on our coordinate grid, our IJ grid, I hope you remember which way is north, east, south and west. Never eat shredded wheat. That's how I remember. So we want to find the time at which the particle is due east of the origin. So we want to find the time when the particle is over here. In other words, when the particle is on the y-axis. Yeah, that's basically what it means. When is the particle on the y-axis or positive y-axis? Well, it's on that axis when the j part of its position is 0, because anywhere on here is going to be something I 0j. So basically it's when the j component or the j part is 0. So what we need to do is to work out a final position where the j part is 0. So we're going to be using this again. Final position equals initial position plus displacement. Now our final position is going to be something at the top. We don't know what its x position is, but we do know that its y or j position is 0, so we can put 0 in there. Its initial position was still the same as before, 3, 7. And we want to know how long. Still the same velocity, 2, -1. And we want to work out what t is. So if we look at the bottom row here, that gives us this 0 equals 7 plus -1 times t, which is -t. Right, straight from that we get t. T is 7. Now if we wanted to, we could plug that into this and work out what this x part is. Yeah, so the actual answer, all that we need is that, yeah, it's 7 seconds when it's due east of the origin. That's when this part is 0. If we then needed to work out the position when it's due east of the origin, we wanted to work out the x part, well, we'll just put 7 here and we'd have 3 plus 2 times 7, so 3 plus 14, we'll have 17. So basically it'll be along here at 17, 0 if we needed that bit of information. A particle has this velocity at time equals 0. The particle moves with a constant acceleration. Okay, so that means the velocity is changing. Find the speed of the particle at the bearing on which it is travelling at the time 3 seconds, t equals 3. So just like any SUVAT equation, we're going to write down SUVAT, but next to these things we may be writing down vectors rather than single numbers. So the velocity at t equals 0 is negative 3i plus j. So that's the initial velocity. Negative 3i plus j, which I might write as a vector, negative 3, 1. The acceleration is also a vector, 2i plus 3j. So as a column, that's going to be 2, 3. We want to find the speed of the particle. So you want to work out this final velocity. That's going to be a vector when t equals 3. So what we do now is we decide which SUVAT equation we're going to use, just like normal SUVAT. Now, u, v, a and t is going to be v equals u plus at. Okay, you can see it over here. And we just plug those numbers in. I'm going to do it as a column. So we want to find v, the vector v. So these are all going to be vectors here. Equals u. Now as a column, that's negative 3, 1. Plus at. Well, that's going to be, there's t there. I'll put it in front. It's just a little bit easier. 2, 3. Okay, all we need to do is work that out. So we have negative 3 here, plus 6, which is 3, and then 1 plus 9, which is 10. So what we've now got is the velocity of the particle at 3 seconds. What we now need to do is to take those numbers. We're going to do Pythagoras on it to find a direction, and we're going to do trigonometry on it. Sorry, no, the other way around. We're going to use Pythagoras to find the speed, the size, the modulus of the velocity, and we'll use trigonometry to find a direction. So the speed, which is what they want us to work out, the speed is the modulus of the velocity, which is Pythagoras on 3 and 10. So that's root 109. Now, if they want that as a decimal to 3 significant figures, that will be 10.44, so 10.4 meters per second. And now we want to find the direction. Now, whenever you find a direction of a vector, always draw a diagram. And it's 3 across, 10 up. So especially if you've got a negative part to your vector, then it's really important that you draw it, and the bearing that it's traveling, right? That's where diagram is important, because this is north. The bearing is going to be this angle, and if you didn't have a diagram, you could end up working out this angle by mistake. Yeah. So the bearing, whoops, black pen. Bearing is going to be that angle theta there, which is equal to the tan inverse of, now let's have a look. If I want to find this angle, that's the adjacent 10. The opposite is 3. Opposite over adjacent, 3 over 10. So I need to make sure I am in degrees on my calculator. So shift menu, angle unit, degree. And now I'm going to do tan inverse 3 over 10. And I get 16.699. Normally we would give any angle answer to 1 decimal place, so 16.7. So 16.7 degrees. Okay, so where's our final answers? There's our speed, and here is our bearing. Oh, bearings. We should have a 0 at the front, shouldn't we? 0, 1, 6 or 016.7. So an ice skater is skating a large flat ice rink. At time 0, the skater is at a fixed point O, so that means that they start at the origin, and their velocity is that, so I'll call U, and write this as a column, 2.4 negative 0.6. At time equals 20, so when time equals 20, their velocity is now, I'll call that V, and that's equal to negative 5.6, 3.4. Relative to the origin, the skater has position S, vector S at time t seconds, so this is going to represent their position. I know we've used R before, using S here. Modelling the ice skater as a particle with constant acceleration. Constant acceleration means you're going to be using SUVAT. Find the acceleration of the ice skater. Okay, so the first thing we do, we write down SUVAT, S-U-V-A-T. We're trying to find the acceleration. At time 20 seconds, their velocity is this 5.6 I plus 3.4 J. I'm just writing it I and J for space reasons, but I'm going to use columns in my working. U is this 2.4 I minus 0.6 J. Yeah, we've got three things to find the fourth. So if we've got U, V, A and T, then we're going to use the equation V equals U plus AT. So V equals U plus AT. So you can, I've underlined the things that are vectors. So V, now I'm going to be using columns, negative 5.6 over 3.4, V equals U, which is 2.4 negative 0.6 plus AT, so that's plus 20, so there's my T, and A is what I need to find. Let's call that X and Y. I can write two equations to solve. So the bottom row is going to be negative 5.6 equals 2.4 plus 20x. So I'm going to solve that to find x in a minute. And then the bottom row, 3.4 equals negative 0.6 plus 20y. So I'll use that to solve y in a moment. So the first thing I'm going to do is let's see, negative 5.6. So we're going to take away 2.4 away from that and divide it by 20. So we get negative 2/5 on negative 0.4. X is negative 0.4. For y, solve that equation. We've got 3.4. We're going to add 0.6 to it, then divide that by 20, and we get a fifth. So y is 0.2. So let's write our answer using I and J over here, since we've been dealing with I and J. So the acceleration is negative 0.4 I plus 0.2 J meters per second squared. In part B, it says an expression for S in terms of T. So we want to write S equals something. Now I have U. It needs to be in terms of T, and I've just worked out the acceleration. So UT equals half AT squared. We'll underline the things which are vectors here, and I'll do the working down here. So S equals U. Now U is this 2.4 negative 0.6, so as a column 2.4 negative 0.6 T plus half times A, negative 0.4 0.2 T squared. Yeah, now we could leave our answer like that. I'm going to write it in the form I and J. So my I's are going to be everything on the top row. So that's going to be 2.4 plus half of negative 0.4 is going to be negative 0.2, so 0.2 t squared. So that's what all the I parts are, plus the j parts are going to be negative 0.6 t plus half of 0.2, which is 0.1 t squared j. So I've just written it there in a slightly different form. And part C, it says the time at which the skater is directly northeast of the origin. I'm going to draw a diagram. I always draw a diagram for these questions. So there's my axis. So there's north, there's east. So if they're northeast, they're on this trajectory, yeah, which is actually a 45-degree angle. Now what's special about this line here, northeast? Well, it's the line y equals x. It's the part where the I part of my position equals the j part of the position. The I part of the position equals the j part of the position. In other words, you are northeast when this bit in this bracket equals this bit in this bracket. So northeast means make this bit here equal to this. So that's what we're going to start doing in part C. So that's where we do 2.4t minus 0.2 t squared equals negative 0.6 t plus 0.1 t squared. So it's now about solving this. So let's add, we want to bring everything to one side. So let's add 0.1 t squared. Add 0.2 t squared to both sides, so we end up with 0.3 t squared. If I bring that over here, so if I bring this over, that means taking away 2.4 away from that, so that'll be negative 3, so minus 3t equals 0. Right, let's factorize that. T goes outside the brackets, and then in the bracket we will have negative 3, or I could write it the other way around. Let's write it the other way around so you know what I'm doing. So that'll be 0.3t minus 3. Right, so what values does that give us? It gives us t equals 0. Okay, well, that's at the very start when it's at the origin, so it's here anyway. So, yeah, we discard that solution. The other solution we're going to get is when, and actually, sorry, I should have written here equal to 0 in case you're wondering what's going on. I missed that out. So I should put equal 0 here. Like that, so you know what I'm doing. That came from there, I just missed writing it up. So the other value is going to be when 0.3t minus 3 equals 0. In other words, 0.3t equals 3, or t equals 3 divided by 0.3, which is 10. So that means they're going to be northeast when t is 10, and you can check for yourself. If you substitute the number 10 into here and the number 10 into here, you'll get the same number. That's a useful check, then you know it's northeast. Lastly, part D. Part D says a second skater travels so that they have got position R, okay, equals this. So they've got that position relative to the origin at time t. Show that the two skaters will meet. So the two skaters are going to meet when this skater's position is the same as the other skater's position. And if we can find a value of t that makes this position equal to this position, we know that they meet. Now this other skater, they only have a j part to their position, So you could write 0i plus this. So we need to make this equal to 0, and we need to make this bit equal to 1.1t minus 6, and we should find that we get the same value of t. That means that this skater's at the position 0i, this j at the same time. So we need to solve both. We can't just solve one. So let's look at the I part. So with the skater, the second skater, the I part of their position, so let's do I here, is 0. It's always 0. And the I part of the other skater's position is 2.4 t minus 0.2 t squared. So let's see if we can solve that. So we'll factorize it. So t, and then in brackets we'll have 2.4 minus 0.2 t equals 0. So what will that give us? That will give us t equals 0, and the other value of t, so I'll try and do this on a calculator. I haven't got a great deal of space. So that will be 0.2t equals 2.4. 0.2t equals 2.4. So t will equal 2.4 divided by 0.2. So that gives us 12. T equals 12. Right, okay. Now let's look at the j positions and see what solution we get for that. We must do the I and the j. Just because their I positions are the same doesn't mean their j positions are the same. So if we look at the j position of the second skater, that's 1.1t minus 6, and for the other skater that is minus 0.6t plus 0.1 t squared. So we can put all of that together down here on one side. So we'll have 0.1 t squared, 0.1 t squared, negative 0.6t plus 1.1, so negative 0.6 plus 1.1 will give us 0.5t. Is that right? Yeah, plus 0.5t plus 6 equals 0. Now I've just realised I've made a mistake here. I did negative 0.6 and I added 1.1. This is like a schoolboy error. I need to go back to school. That should be negative 0.6 minus 1.1. So negative 0.6 minus 1.1. And we get, and I'm doing this on the calculator because I don't trust myself, and I get negative 1.7. Right, so here I should have negative 1.7t. Right, so now we will solve that, and I'm going to use the calculator to do that. So menu and A, and menu, let's go down to solve, and it's a polynomial degree 2, and let's type in the coefficients. 0.1. I could multiply everything by 10, by the way, I don't need to. Negative 1.7 and 6, so I'll get solutions of 12 and 5. Right, so I get t equals 12, t equals 5. Right, so there we go. There is one value of t which makes the I positions the same and the j positions the same. So yes, they do meet, and they meet at 12 seconds meet at t equal 12. So let's just highlight the answers. So A was the acceleration of the ice skater, which we wrote here. B was the expression in terms of S, so we could either have this or we could have it written in this IJ form over here. C was the time in which they're directly northeast, and that was 10 seconds. And D, they meet at 12 seconds. Right, you should now be able to do exercise 8A on pages 162 to 164 of the textbook.